Our presentation is based on composite material and the topic is finding out the coefficient of thermal expansion. Our internal guide is Dr. Gautaman Swaminathan, designation Associate Professor, Department Mechanical, presented by Uday, Rudra, Wasim, Ahmed, Department Mechanical, final year. Abstract: fiber reinforced composite are widely used in various defense and commercial applications due to their superior specific stiffness and strength, as well as corrosion resistance. This project provides understanding on the mechanics of composite materials and its application for the design of composite structure. The objectives of this project are to develop an understanding on the mechanics and properties of composite, to use classical and finite element methods for designing of simple beams made of anisotropic composite material. The result will be compared with that of isotropic materials, aluminum and steel. To develop a design method for making carpet plots for stiffness of unidirectional composites. Content: introduction. Second one is composite material defined, why composite material are important, and the last one is composite particle types. Introduction. The earliest man-made composite materials were straw and mud combined to form bricks for building construction. This ancient bridge making process were documented by Egyptian tomb paintings. Wallet and daub is one of the oldest man-made composite materials at over 6,000 years old. Concrete is also a composite material and is used more than any other man-made material in the world. As of 2006, about 7.5 billion cubic meters of concrete are made each year, more than 1 cubic meter for every person on earth. Traditional composites: composite materials that occur in nature or have been produced by civilization for many years. Synthetic composites: modern material system normally associated with the manufacturing industries, in which the components are first produced separately and then combined in a controlled way to achieve the desired structure, properties and part geometry. Composite material defined: a material system composed of two or more physically distinct phases whose combination produces aggregate properties that are different from those of its constituents. For example, cemented carbides, WC and co-binder, plastic molding compounds containing fillers, rubber mixed with carbon black, wood. A natural composite as distinguished from a synthesized composite. Why composites are important? Composites can be very strong and stiff, yet very light in weight, so ratios of strength to weight and stiffness to weight are several times greater than steel or aluminum. Fatigue properties are generally better than for common engineering metals. Toughness is often greater too. Composite can be designed that do not corrode like steel. Possible to achieve combination of properties not attainable with metals, ceramics or properties alone. Composite material types. Composite particles. It is further classified into three types: particle reinforced, fiber reinforced, and the last one is structural. Computational procedure for determination of engineering plastic properties. This is the flowchart: E1, E2, mu12, G12. Stiffness matrix Q12, QXY, matrices of AXY, BXY, DXY. Theta K represented the fiber orientation, ZK, ZK-1, alpha of XY, H. Where E1, E2, nu12, G12, engineering constants of unidirectional layer. Q12 represent principal layer stiffness, theta K, fiber orientation of layer K. Q of XY is transformed layer K stiffness referred to XY system. ZK and ZK-1 location of layer K stiffnesses. A of XY, B of XY, DXY. Laminate stiffness matrices referred to XY system. Alpha of XY. Laminate extensional compliance matrix H. Total laminate thickness. Steps for the determination of engineering properties of multidirectional laminates. Step 1. Enter the engineering properties of the unidirectional layer E1, E2, mu12 and G12. Step 2. Calculate the layer thickness Q11, Q22, Q12 and Q66 referred to the principal material axis by using the following equation. Q11 equal to E1 divided by 1 minus nu1 to nu21. Q22 is given by E2 by 1 minus nu1 to nu21. Q12 equal to Q21 equal to nu21 E1 divided by 1 minus nu1 to nu21 equal to nu1 to E2 divided by 1 minus nu1 to nu21. Q66 equal to G12. Step 3. Enter the fiber orientation or principal material axis orientation theta k of layer k. Step 4. Calculate the transform matrix QXY of layer k referred to the laminate coordinate system XY using the equation Q of XY matrices equal to m square n square q11 plus m square n square q22 plus m to the power 4 plus n to the power 4 whole into q12 minus 4m square n square q66. We obtain the transformed reduced stiffness as a function of principal laminar stiffness, where m is given by cos theta and n is given by sin theta. Step 5. Enter through the thickness coordinates of layer k surfaces zk and zk minus 1. Step 6. Calculate the laminate stiffness matrices A, B and D using the equation Aij is given by summation of k equal to 1 to n qij zk minus z1 bij equal to 1 by 2 summation of k equal to 1 to n qij k bracket zk square minus z square k minus 1 d of ij equal to 1/3 of summation of k equal to 1 to n qij k bracket of z square k minus z cube k minus 1. Carpet float for the coefficient of thermal expansion of 0m/90m/ plus minus 45 degree plies carbon epoxy laminate. The material is AS4/3501-6. Let alpha, beta and gamma be the fraction of 0 degree, 90 degree and plus or minus 45 degree plies respectively, where alpha equal to m divided by m plus n plus 2p, beta equal to n divided by m plus n plus 2p, gamma is given by 2p by m plus n plus 2p. The general constitutive equation for a laminate is matrices of n, m equal to matrices of a, b, b, d into matrices of epsilon into radius of curvature. n m matrices xy plus nt mt xy plus nm mm xy equal to a, b, b, d into matrices of epsilon into radius of curvature of xy. For symmetrics and balanced laminates, bxy equal to 0, axx equal to ayy and mtxy equal to mmxy equal to 0. If the laminate is under pure thermal loading, the constitutive equation is reduces to ntxy equal to matrices axy into alpha txy into change in temperature, that is del T. Let n be the total number of layers of the laminates 0m 90/90n plus or minus 45 degree plies. H be the laminate thickness and hk be the ply thickness. N equal to 2 into m plus n plus 2p, h equal to n into hk, where hk is given by h by capital N equal to h by 2 into m plus n plus twice p. The stiffness matrices ntx, nty, nts is further deriving summation of k equal to 1 to 2 into m plus n plus twice p, qxx, qyy, 0 qxy, qyy 0, 0 0 qsx all into alpha tx, alpha ty, alpha ts into change in temperature into hk, the ply thickness. These are the equation we are deriving deriving to find out qxy 90 degree, qxy plus 45 degree, qxy minus 45 degree. Similarly, coefficient of thermal expansion alpha txy 90 degree plus 45 degree and minus 45 degree. So qfxy equal to 0. These are the values we are taking from the reference book Uday and Mukhopadhyay. By substituting the above matrix in the previous equation, we get the following equation: ntx, nty, nts equal to delta t into h whole of alpha equal to minus 52.74 to 75.60 plus beta into 275.6 minus 52.740 plus gamma 111.43 111.430 into 10 to the power minus 6. So this is how we are getting the equation 2. Now recall the equation 1. ntxy equal to stiffness matrix xy into coefficient of thermal expansion xy delta t. Equation 2 represent the left hand side of equation 1. Now find the stiffness matrix axy of the right hand side of equation 1. So the formula is given by axy equal to hk summation of k equal to 1 to n qfxy. axy equal to h by m ysm into q of xy 0 plus twice n q of xy 90 plus 2p q of xy plus 45 plus 2p q of xy minus 45. The next step is finding out the stiffness matrix xy. We are deriving to find out the values for stiffness matrix axy. By substituting axy and equation 2 into the equation 1, h delta t is going to cancel from both the sides. These are the equation we are getting from the previous equation. We are substituting the values and we are taking as I equal to minus 52.74 alpha plus 275.6 beta plus 111.43 gamma, j equal to 275.6 alpha minus 52.74 beta plus 111.43 gamma, k equal to 142 alpha plus 10.3 beta plus 46.66 gamma, L equal to 2.78 alpha plus 2.78 beta plus 32.26 gamma, M equal to 10.3 alpha plus 142 beta plus 46.66 gamma, N equal to 7.2 alpha plus 7.2 beta plus 36.68 gamma. Alpha Tx, coefficient of thermal expansion, we are reducing the equation by mi divided by km minus L square minus Lj divided by km minus L square into 10 to the minus 6. Then it can be reduced by alpha Tx equal to mi minus Lj divided by km minus L square into 10 to the power minus 6. Similarly, we are going to find the equation for alpha Ty. Carpet plot for the coefficient of thermal expansion of 0m plus or minus 60 plies carbon epoxy laminate. The material is AS4/3501/6. QXY 0 degree, QXY 90 degree, QXY 60 degree and QXY minus 60 degree. These are the values we are taking from the references Uday and Mukhopadhyay. Similarly, we are taking the values of coefficient of thermal expansion alpha Txy for 90 degrees, 60 degree, minus 60 degree. By substituting the above matrix into the previous equation, we get the following: ntx, nty and nts. Recall the equation 1. ntxy equal to stiffness matrix A of xy into coefficient of thermal expansion alpha Txy into delta T. This is similar as we have discussed earlier. Equation 2 represents the left hand side of equation 1. Now find the stiffness matrix A of xy of the right hand side of equation 1. So this is similar, we have already discussed. By substituting the values of stiffness matrix in equation 2 in equation 1, h into delta t is going to cancel from both the sides. So these are the equation we are getting from the previous equation. And similarly, I equal to minus 53.1 alpha plus 199.59 gamma. Similarly for J, K, L, M and N, the equation alpha Tx for coefficient of thermal expansion is reduced by Mi divided by Km minus L square minus Lj divided by Km minus L square into minus 6. Alpha Tx is equal to Mi minus Lj divided by Km minus L square into 10 to the power minus 6. Similarly, we have to find for the coefficient of thermal expansion in the y direction alpha Ty. So these are the graphs we are getting by using MS Excel program from the various equation. So this graph represent carpet plot for the coefficient of thermal expansion of 0m / 90 and plus or minus 45 degree carbon epoxy laminate AS4 / 35016. Alpha, beta, gamma are fraction of 0 degrees, 90 degrees and plus or minus 45 degree plies respectively. In x-axis we are taking fraction of plus or minus 45 degree plies, and in y-axis coefficient of thermal expansion alpha xt. In x-axis we are substituting the values of gamma 0, 0.2, 0.4, 0.6, 0.1 and alpha equal to 0, 0.1, 0.2 etc. So the next graph is represent for coefficient of thermal expansion 0m plus or minus 60 degree plies carbon epoxy laminate AS4 3501/6. In x-axis we are taken fraction of plus or minus 60 degree plies, and in y-axis the coefficient of thermal expansion alpha xt. How the values of thermal expansion is varying from point to point. So these are the same graphs, this one. So these graphs carpet plot for the coefficient of thermal expansion of 0m plus or minus 60 degree for glass epoxy. Here in x-axis we are taking fraction of plus or minus 60 degree plies, and y-axis coefficient of thermal expansion. The values are taken in x-axis we are taken as the gamma values, and the curves represent the changing of coefficient of thermal expansion for point to point. So these graphs carpet plot for the coefficient of thermal expansion 0m, 90 and plus or minus 45 class carbon epoxy laminates. Alpha, beta and gamma are fraction of 0 degree plies, 90 degree plies and 45 degree plies respectively. These graphs represent for coefficient of thermal expansion in y direction. In x-axis we are taken as fraction of plus or minus 45 degrees plies, coefficient of thermal expansion alpha y t y. So this graphs is similar as the previous one. This is the second graphs, this is the third one, fourth one. Thank you.